Welcome to Lecture 16, Internal Forces in Members. In this lecture, we will look at internal forces and the steps for determining internal forces. When designing a structural member, we need to determine the loads acting within the member to ensure that the material can withstand those loads. Now remember, when I say loads, I'm referring to both forces and moments. So let's look at a couple of real-world examples here. The bridge here, and maybe it's intuitive, but why is the beam thicker at the supports? Here, the sign mounted on a pole. Why is the bottom of the beam wider than the top of the beam? And here for this frame, with a winch attached to it, why is the frame reinforced where it is? Well, in each case, the loads have been determined to be higher there. So all other things being equal, there's more material used there to ensure that those loads can be withstood. For the beam shown, suppose we want to determine the internal forces acting on the cross-section of the beam at point B, which is just to the left of the 6 kilonewton force. Okay, so before we go further with that, let me just note that we tend to use the term internal forces and internal loads or internal loading interchangeably. Okay, let's look at point B, and to find the internal loading there, we would first determine the support reactions of the beam by drawing a free body diagram of the beam and solving for those using our equations of equilibrium. We're in 2D equilibrium here. That shouldn't be anything new. After calculating these support reactions, we are going to cut through the beam at point B and draw a free body diagram of the segment of the beam to the left of the cut or to the right of the cut. Now notice that this is very similar to what we did with when we used the method of sections in simple truss analysis. So we're working with the left side of the cut here. So the beam is the left side of the beam to the left side of the cut is drawn here. We calculated a 5 kilonewton support reaction, 5 kilonewtons acting upward at A. And now at the cut, we need to show the loading there, the forces and moment there, and which will represent what was going on internally in the beam. Now, you can liken this to the 2D rigid body support of a fixed support where we would show, and I'll just draw it again out here. Suppose this is our beam. I'm just going to show the cut here at the cut. So normally we would show, from what we've learned so far, we would show a force in the X direction, a force in the Y direction, and then a moment for a fixed support. So that's what we have here when we've cut the middle of this beam. But there's already a convention established for working with beams. Beams are such a common structural member, and these conventions have already been set up, and we're going to follow them to make it easier on us. So what we show, instead of F sub X, F sub Y, and M, we're going to show what's known as the shear force at B, and we denote shear with a capital V. we're going to show the normal force at B, which we denote with a capital N, and then the moment at B, which in beams we call the bending moment. Now notice these line up well with what we've done before. There's my Y component, my X component, and my moment. Okay, but this is the convention that we're going to be using for beams, that you're going to be using for beams as you progress through mechanics. And now we can use our equations of equilibrium to solve for these unknowns. Notice we're 2D equilibrium, so we have 3 equations. We have 3 unknowns, so we could solve for those 3 unknowns easily. So as discussed on the previous slide, and for 2-dimensional cases, our typical internal loads are going to be a normal force, also known as an axial force because it's acting perpendicular to the cut along the axis of the beam, the shear force, which acts along the surface of the cut, and then the bending moment M. Let's go back to the beam that we cut at point B a couple of slides ago, and we were working with the segment of the beam to the left of the cut. And what was prior to the cut, the internal loading, became the external loading that we showed at point B after the cut when we drew the free body diagram of the cut segment. And we showed that loading as a shear force acting downward, a normal force acting away from the beam, and a moment acting counterclockwise. Now, if we look at the beam segment to the right side of the cut, according to Newton's third law, there must be equal and opposite loading present at the cut in this free body diagram, and that is shown here. Notice everything is in the opposite direction of what it is on our original free body diagram over here. And all of these loadings, the direction that they're shown, both on the for the left side of the cut, the free body diagram from the left side of the cut and the free body diagram for the right side of the cut are considered positive. So let's look at that a little more in depth. So let's start with the normal force. If a normal force that is causing tension is considered positive, okay? So going by that definition, what we're showing here on the free body diagram on the left of the left side of the cut, that's a positive normal force. And for the free body diagram for the right side of the cut, an equal and opposite force causes tension for the right side of the beam, so it's also considered positive. Now this isn't intuitive based on what we've done up to now, but this is the sign convention that's in place and widely accepted, and is what we're going to use when we work with beams. Okay, let's look at the shear force. A shear force that tends to rotate the beam segment clockwise is considered positive. So for the segment on the left side of the cut, a downward shear force tends to rotate the beam clockwise. And for the beam segment on the right side of the cut, an upward shear force tends to rotate the beam clockwise. So those are both considered positive. And for the bending moment, let's look at the left side, a bending moment that tends to cause the segment to curve concave upward is considered positive. So on the left side of the cut, I know I've not much left to draw any more red lines here, but this bending moment is going to tend to bend that beam, the left segment of the beam concave upward. And then if you look at it, the same for this equal and opposite moment for the right side of the beam. Okay, so this takes a little getting used to, but it's the convention we're going to use with our work with beams. Here are the steps for determining the internal forces in members. First, if necessary, determine any support reactions you need by drawing a free body diagram of the member and solving for the unknown reactions. This is nothing new. We've been doing this for several weeks now. Next, take an imaginary cut at the place where you need to determine the internal forces. Then decide which side of the cut will be easier to analyze. Very similar to what we did with method of sections in the analysis of simple trusses. Next, draw a free body diagram of the piece of the member that you're analyzing. And remember to show the unknown normal force, shear force, and bending moment, internal loads at the cut surface using the sign convention that we're following. And last, apply the equations of equilibrium to the free body diagram and solve for the unknown internal loads. Again, nothing different than anything we've been doing for the past several weeks.